So in section 2.2, let's move on to the medium, and this section probably is easy section in chapter 2. We'll talk about wired media and wireless media. In wired media, there are three kinds of media, and also in wireless media there are three kinds. I would say three spectrum regions. Okay, so for the wired media, the most popular one will be the twisted pair that have two copper conductors twisted together. And why they are twisted together? Why are they twisted together? Why? Because that will prevent electromagnetic interference. So that if you twist it, if you have more twist per inch, okay, more twist per inch, then you will be more immune to interference. More immune to interference. So there's a table here showing the so-called category, different category of the twisted pair, from category 1 to category 7. And the category 7 means, well, the higher the category, the more twist per inch, and more immune to interference. And usually we use category 5 for Ethernet. However, if you go for very high speed, then you would use category 6 or 7. Okay, and of course, the more twist per inch you have, the more expensive the line, the cable is. Okay. And the traditional telephone line is only category 1 or 2, so it has barely very few twists per inch. So it wouldn't it wouldn't go far. So you wouldn't use a traditional telephone line to do high speed bit rate and far. So you can go to high speed, but in short distance. If you go longer distance, it wouldn't scale. So that's the way you twist two copper wires. And then still there are two variations. One is shared twisted pair, and the other will be unshared twisted pair, STP and UTP. And the shared twisted pair says that there is another metal shield to cover the twisted pair. And the purpose is to prevent interference, further prevent interference. So it's like a guard, a guard shield that protects the twisted pair. So the quality will be better than the unshielded twisted pair. And usually, compared to the twisted pair, another wire media is the coaxial cable, and it usually is more expensive and provide better quality than the twisted pair. If the twisted pair is for like several hundred meters, or within several at most to several kilometers, then the coaxial cable can go several tens of kilometers. Okay, and there's a inner conductor, which is copper, and then an insulator to protect this inner conductor. And then there will be another conductor, braided conductor, and then another layer of insulator. Okay. So basically, two wires, one inner, one braided, and they are separated by the insulator. And then this kind of a coaxial cable are used in cable modem, for example, and it's you can find it in at your home for cable TV and cable modem, and they can travel far, and they can carry carry a lot of signals inside. Say you have a lot of TV program and also some data channels. And Ethernet, for example, used to use coaxial cable, used to have standard interface for coaxial cable. But later on, they replaced it with a twisted pair. And the reason is because they find out that in order to travel within, say, 2.5 kilometers, then twisted pair is good enough. If you want to travel tens of kilometers, then twisted pair won't work. You would need a coaxial cable. But Ethernet mostly are within buildings, so you'll be several hundreds of meters or up to, say, 2.5 kilometers. So the twisted pair will be enough. So if you see a Ethernet standard or newer standard recently, you would only see two kind of interface. One is twisted pair, and the other one will be optical. But no new standard on coaxial cable. But they used to use coaxial cable, but not any no more. Optical fiber, which is of course much more expensive than the previous two, and also can carry much more, can offer much more bandwidth. And optical fiber is rely on the light, the light traveling through the optical fiber, and the way it travel will rely on the so-called refraction. As you can see that if these are two medium, if this is, say, this is water and this is air, but in the optical fiber you will have glass. Both are glass, but different density. But in this example, we see water and air. Of course, their density are different. Then if you have light coming in from this direction, then it will pass through. And again, for the blue line travel with comes in with this angle, then it would fail to penetrate. It will fail to have the refraction into the air. Okay, and if the angle is even larger, then it would have a total refraction. No more refraction, but reflection. So that's called total internal reflection. So your light coming in with a large angle, it would not penetrate into the other media, and then it will have internal refraction back. And so within optical fiber, you rely on internal total refraction to carry the signal by the light. So here is the structure of a fiber. You have a core, which is plastic or glass. Okay, and then you have a cladding, which is also glass, but different density. It will have different density, and then a jacket to protect. And so you have two medium and how is the refraction work? How does the refraction work here? You have two kinds. So for example, this kind of you have the core, which is thick. You have thick core, and then a thinner cladding. And what you have is that you have, if the angle is large enough, the angle is large enough, then the light will be refracted back. And then here because the angle is large enough, so you have another internal refraction. So if you travel, if this is thick enough, then you would have the signal will propagate through a series of internal refraction. However, this kind of internal refraction will degrade the signal, because every time you have refraction, you lose some energy. So the quality, the signal quality on multimode fiber would not be as good as this kind of fiber. For this, if this is called multimode, the reason it's called multimode is because you would have light traveling in different angle. So the red line with this angle and the blue line in this angle, and each angle will represent one mode. So you have multi-mode, and each of them is having internal refraction within the core. However, if the core is thin enough, okay, then you don't need to rely on total refraction. The lights can travel in straight line, almost straight line. And the virtue of traveling in straight line is that you have less energy loss compared to the internal refraction, that you would have some energy loss. So this will provide you a pretty good quality that you can travel far in this kind of single mode fiber. And again, because there's only one kind of angle, so it's called single mode fiber. And of course, single mode fiber is better but more expensive, because in order to manufacture the fiber with a very thin core, it takes better manufacturing skill and also the material. So it's much more difficult to produce the single mode fiber, and they are more expensive. Okay, so I just have one slide to show the wireless medium, but the text has more to say. The wireless medium, again, we have three kinds of medium. One from the low frequency radio, the radio spectrum, and to the middle spectrum, middle frequency, that's microwave, and to the high frequency, that's infrared. So three kinds within this spectrum, depending on the frequency. Okay. And they can also propagate in three types, three kind of propagation method. One is the ground propagation, and sky propagation, and line of sight. The ground propagation could usually can travel and cover the entire space near the ground area. And the sky propagation would rely on between the sky needs to be high in the sky with much less obstacle in between. And line of sight is even further that you need to pinpoint, the transmitter and receiver need to pinpoint each other. So it's quite directional that you need to know where your sender is. And you tune the receiver to face the sender. And there should be nothing in between. That's line of sight. And this three propagation method has some relationship with the frequency. And the general principle is the higher frequency you go, if you use higher frequency, then you can get higher bandwidth and at higher bit rate. Higher frequency usually mean higher bandwidth and higher bit rate. However, more directional or unidirectional. And when you have that kind of directional property, it means that you lost mobility. So you need to stand still and facing each other in order to transmit at that high frequency. So you lost mobility. Okay, but if you go to the low frequency, then you got a lower bandwidth, lower bit rate. However, it's more so-called omnidirectional, O-M-N-I, omnidirectional, and you have good mobility. So then we should look for a balanced area that you have pretty good enough frequency, a good enough bandwidth, good enough bit rate. However, you still want to maintain the good mobility. And that's the area in microwave and around between 800 megabit per second to something like 2 gigahertz. 2 gigahertz to 800 megahertz. Okay, but if you go to 10 gigahertz, then it's quite directional. So most mobile systems, they use this area between several hundred megahertz to several 2 or 3 gigahertz. Okay, in this area, and that's the microwave area. And within the microwave area, there's an area which is called ISM band, which is unlicensed. You don't need to apply a license to use that area. It's called ISM, and it's around 2.4 gigahertz, and that's the area, the spectrum area that wireless LAN use. For example, we have wireless LAN AP everywhere. And you might wonder, do they got license? No, they don't get license. They don't need to apply the license because it's in the ISM band, and it's free to use. Okay. So within that area, you got good enough bandwidth and bit rate, but still keep the mobility, which is good. We need that. But if you go to 10 gigahertz, you got high bandwidth, high bit rate, but you lost mobility. Okay. So that's the property of a wireless medium. So then if the bandwidth is high, then you need to rely on line of sight propagation. You can't do ground propagation or sky propagation anymore. You need to pinpoint. The antenna, the sender and receiver need to point to each other when you have that kind of high frequency. So like infrared, which we use at home, your remote control is it use infrared. Okay, so you need to point if there's something between somebody standing between you and the TV, then your remote control doesn't work. It doesn't bypass the obstacle, okay, because of its high frequency.